So just one comment. At the very end of last class, I talked a little bit about indicial notation, and I sort of erased, that part is on the previous notes. I've sort of erased it here. This was the last slide minus that part because I wanted to leave some room for some other stuff on this slide. But just one comment about the indicial notation is that I will readily switch between indicial notation and vector or matrix notation whenever it's convenient for me, okay? So you need to be comfortable with both, the indicial and or vector. For the most part, I try to stay in vector and matrix notation, but when we need very explicit clarity on what the individual components are, then I'll switch to indicial notation. So, and I'll sort of do it without warning. So just, be aware of that, okay? So, this is the sort of picture that we had at the end of last time, and really I did nothing but draw vectors, right? I chose a point that can be referenced with the vector x in a reference configuration, and I chose a point q in the reference configuration. And there is a relative vector between these. Q minus x is that vector there, right? And then we're going to track those points through time as our body's deforming, so that in the current configuration we have x, little x and little q, and they also have a relative vector between them, right? And keep in mind what we're trying to do here with these kinematic measures is trying to come up with a mathematical way to track line segments from one configuration to the other, because those line segments, or specifically the changes in the line segments, will give us a measure of deformation, right? And that's sort of what we're after. But so far, we've just done nothing but write down vectors, right? X, Q, U, that's a function of X, and U, that's a function of Q, right? And with that, we came up, we can write down these two equations, right? That little x is clearly a function of big X and U, right? And so now let's write down what this vector is over here. So Q minus x is U of Q minus U of x plus x minus Q. Okay? Well, didn't really mean to do that in red. There's nothing special about that equation. But so we've written this down, and I've dropped the t's. I mean, everything's a function of time except the reference. The reference position x and q, big X and big Q. They're not functions of time, because that's what we chose as the reference position at time t equals 0, right? But everything else, the displacements, little x, little q, they're all functions of time, but I'm just not going to carry around that time variable, okay? So it's always a function of time. Keep that in mind, but I've dropped the notation. All right? So, ultimately we'll see that our field equations are partial differential equations. They deal with infinitesimal quantities, right? So what we're trying to do here is develop a mapping between the reference and the deformed configuration that's some function of the displacements, right? And so let's just take this equation we wrote down and do a Taylor expansion about the point Q equal X. Right? So we're gonna Taylor expand this equation about the point Q equal X. And here I'm going to switch to indicial notation, because remember, these are all vectors, right? So we're doing a Taylor expansion of vectors, and so you have to go back to Calc 3 to remember how to do this. Okay, so I'm going to write everything out. I have the ith component here, qi minus xi plus ui xj qj minus xj plus, sorry, I. By the way, occasionally when I'm writing a long equation, I'll try to just be quiet, not say anything while I'm writing it. And then what I can do when I post-process the videos, I can squeeze that down. So you don't have to watch me write a long equation, right? So I can squeeze a minute long write to 10 seconds, right? You know. So if I think about it, I'll do that. It'll save you some time when you go back and reference the videos. Okay, so I wrote that out in component form, and I can simplify it a little bit more if I use something called a Kronecker delta function. So in additional notation, we have this thing called a Kronecker delta function, which takes on the value 1 when I is equal to j and 0 otherwise. So it's sort of when you go from at least when I and j are equal, which is usually the case in Cartesian coordinates with what we're dealing with, then when you go back to the vector matrix notation, this Kronecker delta function sort of becomes the identity matrix, right? So one thing we can do with it is, you can use it to basically, I can have that. Well, let's just use, I don't want to, this is just sort of in general, the ith component of a vector can also be written as the Kronecker delta times the jth component. So in this case, if you just work through the details, because only when I equal to j is it going to be non-zero. And so what this does is it sort of, anytime you see this, the Kronecker delta multiplied by a vector, and you have a repeated indice, remember that's like a summation, you can pass over that repeated indice such that this is just AI, okay? So you can use these Kronecker deltas to manipulate equations. And what I'm going to do is I'm going to use that Kronecker delta to turn them into j's. So basically, implicitly what I'm going to do is I'm going to say delta ij qj minus delta ij xj. That's equal to qi minus xji. Right? So this is what I'm doing here, but I'm going to sort of do it in one step. Is I'm going to say delta ij multiplied by qj minus xj plus terms that are on the order of the magnitude of q minus x. Right? And so now you see I have a qj minus xj in both terms. So finally I'm going to pull this out and say delta ij plus ui xj times qj minus xj plus higher order terms. Well, I kind of ran out of room here, and I didn't want to. I'll use a different color to try to make this obvious, right? So again, we're trying to, what we're trying to do is come up with a mathematical description that takes line segments in the reference configuration into line segments in the deformed configuration, right? And so what if we give these line segments a name, like these red vectors I drew here, right? So because we did a Taylor expansion about, when q and x are infinitesimally close to one another, right? About the point q equal to x, let's give this line segment a name. And since it's an infinitesimally kind of small line segment, let's just call it dx, d big X, okay? So it's a vector, right? An infinitesimally small vector in the reference configuration. And we'll give this one a name, d little x, right? An infinitesimally small vector in the deformed configuration. Okay, and so then what we have is that if I just remember, so this is d little x, this is d big X, right? So I have d little x equals to this thing, and I'll go ahead and just rewrite it on the next page. So what we have is d little x is equal to, and I'll keep it in component form, delta ij plus xj d big X j plus terms that are on the order of dx squared. Everybody okay with that? Right? So we just wrote down the equation, Taylor expanded about q equal to x, and then just gave these vectors q minus x, big Q minus big X, and little q minus little x new names. They're just vectors, right? So we just gave them new names, and this is the result down here. Which I've rewritten there. All right. So this thing, right, has a name. We call it the deformation gradient. It's a tensor, second order tensor, or a matrix in 2D, I mean in 3D. In Cartesian coordinates. We call it the deformation gradient. Right? And this is sort of the fundamental kinematical description of motion. It's a first order description of motion, deformation, okay? And first order because, you're right, we're ignoring terms on the order of, because this is an infinitesimally small vector, then it's a good approximation to just ignore those higher order terms, right? And so we're left with is this equation, or if we write it in vector form, d little x is equal to f d big X, right? Where d little x and d big X are vectors, and f is a matrix, right? Where you can clearly see it's a linear operator, right? It takes vectors in the reference configuration, d big X, infinitesimal vectors in the reference configuration, into infinitesimal vectors in the deformed configuration, right? And it's a first order approximation of that. So just